Hi and welcome to John's Maths book. In this video, we're going to be looking at the separation of variables technique to solve first order differential equations. If you like the video, then please hit the like button and I'd be delighted and honored if you'd subscribe to the channel. Without further ado, let's go over to the whiteboard. We can use a technique called separation of variables to solve first order differential equations of the form shown on the board. dy dx equals a function f of x multiplied by a function g of y. F of x only contains the variable x and function g of y only contains the variable y. To solve this type of differential equation, we take all the terms involving y, including dy, to the left-hand side of the equation, and all terms involving x, including dx, to the right-hand side of the equation. We can then integrate the left-hand side of the equation and the right-hand side of the equation to find a solution for y. An example of where we could use this technique would be to solve a differential equation such as dy by dx equals x divided by y. In this case, f of x is equal to x and g of y is equal to 1 divided by y. And the two functions are multiplied together to give x over y. This technique could not be used to solve a differential equation such as dy by dx equals x plus y, because however hard we try, we cannot get it into the form f of x times g of y. Note in some cases, we will need to manipulate the differential equation to get it into the form f of x times g of y. When solving first order differential equations, try this method first before looking at other methods of solution. So now let's look at some examples of using this method to find the general solution of first order differential equations. In the next video, I'll look at the same method to find a particular solution to differential equations. So first up, we want to solve the first order differential equation. Dy by dx is equal to 3x squared divided by y. In this equation, we can see that it fits the model where a function f of x is multiplied by a function g of y. In this case, f of x is 3x squared and g of y is 1 divided by y. When the two are multiplied together, we get 3x squared divided by y. If we now separate the variables and move all terms involving y to the left-hand side and all terms involving x to the right-hand side, we're left with y dy equals 3x squared dx. We can then integrate both sides to find a general solution to the differential equation. So starting by integrating the left-hand side, the antiderivative of y is y squared divided by 2 plus a constant of integration, let's call it c1. And then integrating the right-hand side, the antiderivative of 3x squared is x cubed plus a constant of integration, let's call it c2. If we now subtract the constant c1 from both sides and multiply both sides by 2, we're left with y squared equals 2x cubed plus 2 times, and then in the bracket c2 minus c1. If we now substitute the value of c for c2 minus c1 multiplied by 2, we're left with y squared equals 2x cubed plus c. And taking the square root of both sides, we're left with y is equal to plus or minus the square root of 2x cubed plus c. So this gives us the general solution to the differential equation. Now let's look at another example. Let's find the general solution to the first order differential equation. Dy by dx equals x times y plus 2 minus 2x minus y. To use the separation of variables technique to solve this differential equation, the first thing we need to do is ask whether we can get the right-hand side into a form where we have a function of x multiplied by a function of y. With some algebraic manipulation, which I said we might need, we can rewrite this equation as dy by dx is equal to x minus 1 multiplied by y minus 2. In this form, f of x is clearly defined as x minus 1 and g of y is clearly defined as y minus 2. We can now separate the variables by moving all the terms involving y to the left-hand side and all the terms involving x to the right-hand side. So we're left with 1 divided by y minus 2 times dy is equal to x minus 1 dx. We can now integrate both sides to find the general solution to this differential equation. So starting with the left-hand side, the antiderivative of 1 divided by y minus 2 is the natural log of the absolute value of y minus 2 plus a constant of integration, let's call it c1. And on the right-hand side, the antiderivative of x minus 1 is x squared divided by 2 minus x plus a constant of integration, which we'll call c2. We can now subtract c1 from both sides of the equation and let constant c3 equal c2 minus c1, and we're left with the natural log of the absolute value of y minus 2 is equal to x squared divided by 2 minus x plus c3. Exponentiating both sides, we're left with y minus 2 is equal to e to the power of x squared divided by 2 minus x plus c3. If we rewrite e to the power of x squared divided by 2 minus x plus c3 as e to the power of c3 multiplied by e to the power of x squared divided by 2 minus x, and then add 2 to both sides of the equation, we're left with y equals 2 plus e to the power of c3 times e to the power of x squared divided by 2 minus x. If we now tidy this up a bit and let c equal e to the power of c3, we're left with y equals 2 plus c times e to the power of x squared divided by 2 minus x. And this is the general solution of the differential equation.